The research paper delves into the faster convergence of atom compared to stochastic gradient descent, SGD, for transformers, introducing the concept of directional sharpness. It postulates that the performance of optimization algorithms is intrinsically linked to the directional sharpness of the update steps. A comparative analysis reveals that SGD exhibits poorer directional sharpness in contrast to adaptive algorithms. The authors identify that a small fraction of the coordinates are responsible for the suboptimal sharpness and slow convergence of SGD. They propose coordinate-wise clipping as a potential solution to this issue. Through various experiments, they demonstrate the efficacy of coordinate-wise clipping in reducing sharpness and accelerating the convergence of optimization algorithms. This study suggests that the sharpness reduction effect of adaptive coordinate-wise scaling is the primary reason behind ATOM's superior performance in practical applications. Furthermore, it advocates for the use of coordinate-wise clipping as a universal technique to expedite deep learning optimization. The research focuses on optimization algorithms in deep learning, specifically examining the local geometry of transformers. It highlights that adaptive algorithms, such as ATOM, exhibit lower directional sharpness compared to stochastic gradient descent, SGD, which is a key indicator of their superior performance. The paper introduces coordinate-wise clipping as a technique to improve directional sharpness and convergence speed by preventing a few coordinates with large gradients from dominating the update direction. Experiments demonstrate the effectiveness of clipping across tasks, models, and iterations, suggesting that the optimization algorithm's landscape in local geometry is a useful proxy for global convergence speed. The convergence rates of ATOM compared to SGD are discussed, highlighting the gap in theoretical understanding despite ATOM's empirical fast performance. The use of coordinate-wise clipping, particularly in transformers, is explored, where it outperforms ATOM. The concept of directional sharpness is introduced as a new measurement to indicate the performance of optimization algorithms, emphasizing its relation to fast convergence. The section concludes by discussing the quadratic Taylor expansion of the objective function, focusing on minimizing gradient correlation and directional sharpness to achieve better optimization. The concept of L-smooth functions plays a crucial role in optimization proofs, particularly in deep learning. The local Hessian spectral norm, also known as the sharpness of the function, is a key factor. The introduction of directional sharpness, focusing on the specific update direction of an optimization algorithm, emphasizes the importance of this direction in achieving fast convergence. It is argued that minimizing directional sharpness is more critical than minimizing gradient correlation for efficient optimization. This discussion highlights the significance of the update direction in the optimization process, especially when compared to adaptive algorithms. The authors investigate the sharpness of different optimization algorithms, including SGD, ATOM, Adafactor, and Lion, on machine translation tasks. They observe that adaptive algorithms like ATOM and Adafactor have a lower sharpness ratio compared to SGD, indicating they can use a larger step size and achieve a lower loss. Figure 1 shows the histogram of update step distribution over coordinates for SGD, ATOM, and Adafactor, revealing an uneven gradient distribution across coordinates. Half of the coordinates have absolute values ranging from 10^12 to 10^6, while a small fraction of coordinates have values as high as 10^4 to 10^2, contributing significantly to the gradient norm. This imbalance makes optimization challenging. The authors propose coordinate-wise clipping as a solution to this imbalance, demonstrating in Table 1 that clipping improves the directional sharpness of optimization algorithms. They also investigate the relationship between the sharpness reduction effect of adaptive algorithms and the distribution of gradient norm across different coordinates, finding that adaptive algorithms are less affected by the imbalance in gradient distribution, leading to better convergence rates. The research applies coordinate-wise clipping to various optimization algorithms for machine translation tasks, aiming to reduce adaptive algorithm sharpness and speed up optimization. Clipping is applied to the top k% gradients at each iteration, updating the momentum term with the clipped gradients. This approach significantly reduces directional sharpness and improves efficiency, particularly for ATOM and Adafactor where coordinate-wise scaling is already implemented. The results are visualized in figures, showcasing loss landscapes and optimization progress under different clipping conditions. The application of coordinate-wise clipping in optimization algorithms like SGD and ATOM is explored to enhance their performance on sharp minima. Clipping gradients is presented as a universal technique in non-coordinate-wise scaling algorithms to improve training speed. The paper discusses the implementation of clipping in different algorithms, including detailed descriptions of modified algorithms, and visualizes the loss landscape for autoregressive language modeling tasks. Experimental results demonstrate that clipped algorithms converge faster than their original counterparts, as shown in Figure 6. The authors suggest that clipping can be used universally in any non-coordinate-wise scaling algorithms and propose a connection between coordinate-wise smoothness and the success of ATOM. The paper revisits an example where f(x) equals x(tx) and argues that clipping allows for a larger learning rate by preventing gradients from becoming too large. Convergence properties of optimization algorithms are critical in machine learning. This research focuses on clipped optimization methods, comparing their loss convergence with that of original algorithms such as stochastic gradient descent, SGD, ATOM, ADAFactor, and Lion. Figures and tables illustrate the superior convergence of clipped optimization algorithms, indicating faster convergence rates compared to their original counterparts. This finding is consistent with the landscape analysis, which suggests that local geometry performance is a reliable indicator of global convergence speed. Furthermore, the concept of coordinate-wise clipping is introduced, demonstrating its ability to improve convergence by mitigating imbalanced distributions of gradients. Theoretical justification for gradient clipping in non-convex optimization is provided through an informal theorem, highlighting its benefits in removing exploding gradients and improving convergence. In the experimental setup, a fair comparison is ensured by selecting various optimization algorithms, including clipped and unclipped versions. This comprehensive evaluation provides a thorough understanding of the convergence properties of different optimization algorithms. By analyzing the convergence rates and loss landscapes of these algorithms, this research contributes to the development of more efficient optimization methods for complex machine learning tasks. The results have significant implications for the optimization of deep neural networks and other non-convex problems. In the realm of deep learning optimization algorithms, adaptive methods like ATOM have consistently outperformed traditional stochastic gradient descent, SGD. This paper sheds new light on the reasons behind ATOM's superior performance, positing that directional sharpness is a crucial indicator of an algorithm's efficacy. The authors contend that high directional sharpness, resulting from a positive coordinate-wise gradient Hessian correlation, is responsible for SGD's slow convergence. To mitigate this issue, they propose coordinate-wise clipping, a technique that reduces sharpness and accelerates convergence speed. This approach can be seamlessly integrated into various optimization algorithms, including SGD, normalized SGD, and ADAFactor, without requiring coordinate-wise scaling. The study's empirical evaluations in machine translation and autoregressive language modeling tasks demonstrate that clipped algorithms generally exhibit better directional sharpness and faster global convergence compared to their non-clipped counterparts. The findings underscore the importance of understanding ATOM's empirical advantage over SGD and suggest that coordinate-wise clipping may be a universally applicable technique to expedite deep learning optimization algorithms. This section of the research paper provides a comprehensive overview of various optimization methods and their applications in machine learning. It begins by discussing the importance of optimization algorithms in large-scale machine learning, citing Leon Batu et al.'s work on optimization methods for large-scale machine learning. The authors then delve into stochastic gradient learning in neural networks as introduced by Leon Batu et al., which has been a cornerstone for many subsequent advancements in the field. The paper also explores other optimization techniques, highlighting their strengths and limitations in different scenarios. Stochastic optimization is a crucial area of research, with numerous papers contributing to its advancement. A seminal work by Kingma and Ba, ATOM, a method for stochastic optimization, introduced the ATOM optimizer, which adapts learning rates for each parameter based on the magnitude of the gradient. This approach has been instrumental in enhancing optimization efficiency. Another significant contribution comes from Li and Oribona's paper on the convergence of stochastic gradient descent with adaptive step sizes, which provides insights into the convergence properties of stochastic gradient descent, SGD, with adaptive learning rates. This work highlights the importance of adaptivity in optimization algorithms. Building upon these findings, Polyak's work on Introduction to Optimization offers a comprehensive understanding of the convergence properties of algorithms like ADAM and AdaClip. These algorithms have been shown to exhibit superior optimization efficiency, particularly in scenarios with noisy or sparse gradients. The significance of adaptive learning rates is further underscored by papers from Shazir and Stern, and Reddy et al., which demonstrate the profound impact of adaptivity on optimization efficiency. These works collectively emphasize the need for adaptive learning rates in stochastic optimization, leading to improved convergence rates and accelerated optimization. This body of research provides a comprehensive overview of the current state of stochastic optimization techniques and their applications. The collective contributions of these papers have significantly advanced the field, offering insights into the development of efficient optimization algorithms and their applications in various domains. Building upon the concept of attention introduced by Vaswani et al., which eliminates the need for recurrence and convolution in machine translation tasks, the authors draw inspiration from adaptive gradient methods, such as AdaGrad, that adjust the learning rate based on the gradient norm. Coordinate descent algorithms, which iteratively update parameters in a cyclical manner, are also relevant in this context. The importance of gradient clipping in deep learning is highlighted, citing Zhang et al., who provide a theoretical justification for adaptivity in gradient clipping. The effectiveness of adaptive methods in attention models is demonstrated by Zhang et al. The authors then explore the convergence properties of adaptive gradient methods for non-convex optimization, citing Zhou et al. And Zhou and Shen, who analyze the convergence of adaptive gradient methods with momentum for training deep neural networks. These works provide theoretical guarantees for the convergence of adaptive methods in non-convex settings. The author's discussion revolves around the interplay between attention mechanisms, adaptive gradient methods, and gradient clipping in deep learning, aiming to provide a comprehensive understanding of the convergence properties of these methods, particularly in the context of attention models. By examining the convergence properties of these methods, the authors seek to establish a deeper understanding of the complex interactions between attention, adaptation, and gradient clipping in deep learning. The convergence of clipping with coordinate-wise smoothness is formally proven, assuming the function f is non-convex and L-smooth. The existence of a specific epsilon in L is demonstrated, ensuring the remaining Hessian after removing an epsilon fraction of coordinates has a spectral norm at most L. The gradient is also assumed to be uniform, with the clipped part not being too large. This is crucial for the clipping algorithm's operation, preventing edge cases where the gradient in the unclipped coordinates becomes too imbalanced. The gradient norm is further assumed to be large compared to the clipping threshold quart. The gradient descent lemma is then presented, establishing an expected loss decrement with respect to the norm of the gradient. This is achieved through SGD that clips the top delta fraction, with a step size eta greater than or equal to 2L. The proof involves defining matrices and bounding the directional sharpness, demonstrating an upper bound of O, square root epsilon L plus L, compared to L for SGD. The authors establish the gradient descent lemma, a fundamental result in stochastic gradient descent, by deriving an upper bound on the difference in function values between consecutive iterations. This bound is expressed as f, xt plus 1, is less than or equal to f, xt, eta nabla f, xt, gt plus 1 half eta squared gt squared f, xt, gt, which is then simplified through algebraic manipulations to f, xt plus 1, is less than or equal to f, xt, eta parallel gt squared, 2 plus eta squared, square root epsilon L plus L, 2, square root dct parallel gt squared, and further to f, xt plus 1, is less than or equal to f, xt, eta parallel gt squared, 2 plus eta squared, square root epsilon L plus L, 2, c squared gt squared, assuming gt is uniformly distributed. By choosing an optimal learning rate eta equals 1, 2 square root epsilon L plus L, C squared, the authors obtain f, xt plus 1, is less than or equal to f, xt, 1, 4 square root epsilon L plus 2L, C squared gt squared is less than or equal to f, xt, C squared, 4 square root epsilon L plus 2L, C squared f, xt, squared. This result is compared to the standard gradient descent case, where the optimal learning rate is eta equals 1 per liter, yielding f, xt plus 1, is less than or equal to f, xt, 1/2 L parallel nabla f, xt, squared. The author's proof of the gradient descent lemma for stochastic gradient descent with clipping highlights the importance of clipping in achieving a tighter bound on the learning rate. The experimental details of the study focus on tasks, datasets, and models. For machine translation, the English to French Opus Books dataset is used with the T5 small model. For autoregressive tasks, the GPT-NEO model is employed, pre-trained on the code Clippy dataset and using the StackSmol version of the Stack dataset. The batch size for machine translation is 1024, with a training set size of 10,240. Resulting in 10 batches per epoch. In contrast, the batch size for autoregressive tasks is 1000. No test or validation sets are used, and the sole evaluation metric is the cross-entropy loss. 6 optimization algorithms are utilized, including ATOM, SGD, Sine SGD, Normalized SGD, ADDFactor, and Lion. Momentum is incorporated into all algorithms to eliminate any potential momentum effects. The clipping function, clip, g, calculates the clipping threshold tau for the top k% coordinates and returns g, where g equals SGN, gi, min, gi, tau. A large fraction of 10% and 50% is used for non-coordinate-wise scaling algorithms and adaptive algorithms, respectively, to demonstrate the effectiveness of clipping. The clipping methods are applied to the gradient in the nominator of the final update step for ATOM and ADDFactor, as clipping the entire gradient could cancel out or increase the norm. The refined version of the transcript starts directly with the content, focusing on the algorithms for optimizing neural network parameters. It begins by detailing algorithm 4, which presents a normalized SGD with momentum for weight matrices and vectors. This involves a learning rate, momentum term, and gradient clipping. Next, it discusses algorithm 5, introducing sine SGD with momentum, which uses the sine function for the gradient update. The text then moves on to algorithm 6, describing ATOM, which incorporates momentum and second moment estimates for adaptive learning rates. Finally, it discusses algorithm 7, ADDFactor, a method specifically designed for weight matrices, featuring relative step sizes and second moment decay. Throughout, the focus is on improving training efficiency and stability in neural networks. The optimization methods presented in algorithms 8 and 9, ADDFactor and Lion, respectively, demonstrate distinct approaches for weight vector optimization. ADDFactor takes an initial point x0, relative step sizes ρt, and regularization constants e1 and e2 as input. It iteratively updates the learning rate alpha t, gradient estimate gt, and variance estimate vt, clipping the gradient to prevent exploding gradients and computing the variance estimate using the clipped gradient and second moment decay, beta 2t. The update direction UD is computed as the ratio of the clipped gradient to the variance estimate, followed by clipping to prevent large updates. The final update is performed using the learning rate alpha t and the clipped update direction UD, iterating for t steps with decreasing learning rate alpha t. In contrast, Lion uses a different approach, taking the current iterate xt and stochastic gradient gt as input. It computes the update direction UD using a momentum term mount and a sine function, updating the momentum term using the current gradient and a decay rate beta 2. The final update is performed using the learning rate eta and the update direction UD. Both algorithms adapt to the optimization problem's geometry, with ADDFactor using a diagonal Hessian approximation and Lion employing a momentum-based approach. The choice of algorithm depends on the specific problem and computational constraints. The experiment on directional sharpness of optimization algorithms involves computing the momentum term using a pseudo-update step for all algorithms, regardless of the optimization algorithm used for the actual update step. This is done to visualize the landscape and compare sharpness. Different training optimizers, such as SGD momentum and atom, are used to compare results across different local geometries and optimization trajectories. A test batch of 1024 is sampled to speed up the visualization process. For landscape visualization, the weight is updated with the desired update step, and the loss is computed before resetting the weight to its original value. The directional sharpness is computed using PyTorch's Hessian vector product, ensuring positivity by using a robust version of the formula in rare cases of negative sharpness. This table provides a comprehensive overview of the learning rate configurations for various experiments conducted in the research. The table is organized by task, focusing on machine translation and autoregressive tasks. For each task, different algorithms are listed along with their corresponding learning rates. These algorithms include stochastic gradient descent, SGD, stochastic gradient descent with gradient clipping, SGD, clipgrad, atom with gradient clipping, atom, clipgrad, attafactor with gradient clipping, attafactor, clipgrad, lion, sine SGD, and normalized SGD. The learning rates range from 1 × 10⁻⁵ for the autoregressive task using stochastic gradient descent to 3 × 10⁻² for the machine translation task using attafactor with gradient clipping. Notably, the relative learning rate for attafactor is defined in algorithms 7 and 8, as well as in the reference, 43. This table provides a clear overview of the experimental setup and parameter tuning for the different algorithms tested, allowing researchers to easily compare and contrast the performance of these models under various conditions. This section presents the experimental results for the directional sharpness of optimization algorithms, showcasing the landscape visualization of machine translation in SGD trajectory at epoch 2. The plots display the optimization trajectories of various algorithms, including SGD, atom, attafactor, lion, sine SGD, and normalized SGD, with and without gradient clipping and update clipping. These experiments were repeated with 3 random seeds to ensure reliability. The z-axis represents the step size, and the y-axis denotes the loss. To better visualize the directional sharpness of each algorithm, the plots are scaled differently. The results demonstrate that attafactor exhibits improved directional sharpness compared to other optimization algorithms, particularly in the presence of gradient clipping. The plots also indicate that gradient clipping can significantly affect the optimization trajectory, leading to improved convergence in some cases. Landscape visualization provides valuable insights into the optimization process, enabling the analysis of the directional sharpness of different algorithms. This analysis is crucial for understanding the convergence behavior of optimization algorithms in machine translation tasks. A comparative analysis of various optimization algorithms is presented, including stochastic gradient descent, SGD, atom, and their variants with clipping gradients or updates, as well as attafactor, lion, sine SGD, and normalized SGD. The algorithms are evaluated across 3 experiments, each with distinct step sizes and gradient clipping applications. In experiment 1, loss curves for each optimizer are plotted against the number of steps taken, revealing that clipping gradients at 0.1 significantly improves SGD's performance, while clipping updates at 0.5 enhances atom's performance. Lion and sine SGD also exhibit competitive performance with their respective clipping strategies. Notably, normalized SGD shows promising results when combined with gradient clipping at 0.1. Experiment 2 demonstrates similar trends but with smaller step sizes, resulting in a less pronounced performance gap between optimizers. This suggests that smaller step sizes may reduce the effectiveness of clipping gradients or updates. In contrast, experiment 3 introduces larger step sizes, leading to more pronounced differences in optimizer performance. Here, clipping gradients or updates becomes crucial for maintaining stability and achieving lower loss values. A landscape visualization of the machine translation task's loss surface in the SGD trajectory at epoch 5 is provided, offering insights into how different optimizers navigate the complex loss landscape and their convergence properties and stability. Overall, These experiments highlight the importance of gradient clipping and update clipping in enhancing the stability and performance of various optimization algorithms, particularly in scenarios where large step sizes are employed. This page presents the results of 3 experiments examining the landscape visualization of machine translation using different optimizers and clipping techniques. The experiments aim to investigate the effect of clipping gradients and updates on the optimization trajectory. In Experiment 1, the authors compare the performance of various optimizers, including SGD, ATOM, ADDFactor, Lion, Sine SGD, and normalized SGD, with and without gradient clipping and update clipping. The results show that clipping gradients and updates can significantly impact the optimization trajectory, with some optimizers benefiting from clipping while others do not. Experiment 2 further explores the effect of gradient clipping and update clipping on the optimization trajectory, focusing on the step size. The results indicate that the optimal step size varies depending on the optimizer and clipping technique used. Experiment 3 visualizes the landscape of machine translation using the SGD trajectory at epoch 10, demonstrating that the optimization trajectory can be complex and non-convex. The experiments use a range of step sizes, from 2.0 to 2.35, and employ different clipping techniques, including gradient clipping and update clipping, with varying clipping values. The results are presented in the form of loss curves, showing the performance of the different optimizers and clipping techniques over the course of the optimization process. Overall, this page provides valuable insights into the impact of clipping techniques and optimizer selection on the optimization trajectory in machine translation, highlighting the need for careful consideration of these factors to achieve optimal performance. This analysis presents a comprehensive examination of the performance of various optimization algorithms in machine translation tasks, focusing on their loss trajectories over epochs and batch sizes. The experiments are conducted with different step sizes to evaluate the efficacy of clipping gradients and updates for each algorithm. The first experiment illustrates the loss trajectories for various optimization algorithms, including SGD, ATOM, Lion, and their variants with gradient clipping and update clipping. It is evident that clipping gradients at 0.1 significantly reduces the loss for all algorithms, particularly in the early stages of training. This suggests that gradient clipping can be beneficial in stabilizing the training process and improving convergence rates. In the second experiment, the loss trajectories are presented for a smaller step size range. The results indicate that a smaller step size leads to more stable loss trajectories, especially when gradient clipping is applied. This highlights the importance of choosing an appropriate learning rate and clipping strategy to ensure smooth optimization progress. The third experiment visualizes the landscape of machine translation in the SGD trajectory at epoch 20. This visualization provides insight into how different optimization algorithms navigate the loss landscape, which is crucial for understanding their convergence properties and efficiency. Overall, these experiments demonstrate the importance of considering both the choice of optimization algorithm and the clipping strategy in machine translation tasks. By analyzing the loss trajectories and landscape visualizations, researchers can gain valuable insights into optimizing their models for better performance and convergence. The table compares the ratio of directional sharpness for various optimization algorithms against SGD on a machine translation task, evaluating each algorithm's performance in 3 experiments. It includes algorithms like 2SGD, SGD, ClipGrad, ATOM, ADDFactor, Lion, Sine SGD, and normalized SGD, both with and without clipping gradients, to highlight their efficiency and effectiveness in optimizing the SGD trajectory. Figure 11 presents a landscape visualization of the autoregressive model's trajectory using stochastic gradient descent, SGD, and various adaptive gradient methods, including ATOM with gradient clipping at 0.5, ADDFactor with gradient clipping at 0.5, and the Lion optimizer. The figure consists of 4 subplots, each corresponding to a different epoch: 2, 5, 10, and 20. The z-axis represents the step size, and the y-axis represents the loss. The plots illustrate the optimization trajectories of the different algorithms, showcasing their convergence patterns and loss landscapes. In the early stages of optimization, Atom and attefactor exhibit more stable convergence compared to SGD, which oscillates significantly. The addition of gradient clipping at 0.5 further stabilizes the convergence of atom and attefactor. As optimization progresses, the differences between the optimization trajectories become less pronounced. However, the Lion optimizer consistently exhibits more stable convergence compared to the other methods. Notably, the step size adaptation in attefactor and Lion leads to more gradual convergence. These visualizations provide insights into the optimization dynamics of autoregressive models, highlighting the importance of adaptive gradient methods and step size adaptation in achieving stable convergence. The results suggest that adaptive gradient methods, such as atom and attefactor, can improve the stability of optimization trajectories, while step size adaptation, as seen in attefactor and Lion, can lead to more gradual convergence. In the realm of optimization algorithms, the epoch algorithm ratio provides a crucial metric for comparing the directional sharpness of various methods against stochastic gradient descent, SGD, on autoregressive tasks. This ratio is calculated for several algorithms, including 2SGD, atom, attefactor, and Lion, with and without gradient clipping, to assess their optimization performance. The analysis presents data for different epochs, specifically 2, 5, 10, and 20, to provide a comprehensive understanding of each algorithm's efficiency. By comparing these ratios, researchers can identify the most effective algorithms for the task at hand, shedding light on the optimal choice for specific applications. The inclusion of gradient clipping in the analysis allows for a nuanced understanding of its impact on optimization performance. This is particularly important, as gradient clipping is a common technique used to stabilize training and prevent exploding gradients. The epoch algorithm ratio serves as a valuable tool for the machine learning community, providing insights into the strengths and weaknesses of various optimization algorithms on autoregressive tasks. By evaluating the directional sharpness of these algorithms, researchers can develop more efficient and effective optimization strategies, ultimately leading to improved performance in complex machine learning models. This page presents a comprehensive comparison of various optimization algorithms in machine learning, focusing on their step sizes and loss values at Epoch 2, Batch 6. 3 experiments are conducted to analyze the performance of these algorithms under different conditions. Experiment 1 illustrates the performance of several algorithms such as SGD with gradient clipping at 0.1, atom, Lion, sine_SGD, and normalized_SGD. The results are presented in 3 different scales: small, medium, and large step sizes. In this experiment, the loss values for each algorithm are plotted against the step size, showcasing how different algorithms behave with varying step sizes. Experiment 2 demonstrates the same algorithms but with different step size ranges. This experiment provides further insight into the sensitivity of these algorithms to step size adjustments. The loss values are again plotted against the step size, highlighting the distinct performance profiles of each algorithm. Experiment 3 presents a landscape visualization of machine translation in the atom trajectory at Epoch 2. This visualization provides a visual representation of the loss landscape, allowing for a deeper understanding of the optimization process and the trajectory of the atom algorithm. The experiments collectively provide a detailed analysis of the optimization algorithm's performance under various conditions. By examining the loss values and step sizes, researchers can gain insight into the strengths and weaknesses of each algorithm, helping to inform future research and practical applications in machine learning. This analysis delves into the performance of various machine learning optimization algorithms, examining their strengths and weaknesses across different scenarios. A comparative study is conducted, focusing on algorithms such as stochastic gradient descent, SGD, atom, and others, over multiple epochs and batches. The data visualization in figures and tables provides an in-depth look at the evolution of step size and loss over time, offering insights into the algorithm's efficiency under varying conditions. This comparison is essential for understanding which algorithm excels in specific situations, thereby aiding in strategy selection for machine learning tasks. Moreover, the impact of clipping gradients and updates on these algorithms' performance is also explored. Clipping gradients can significantly influence the stability and convergence rate of an algorithm, while updates can alter its adaptability to changing data distributions. In conclusion, this section offers a comprehensive overview of the optimization landscape in machine learning, shedding light on the most effective strategies for enhancing model performance. It serves as a valuable resource for researchers and practitioners seeking to optimize their machine learning models efficiently. The results of 3 experiments evaluating the loss landscapes of machine translation models trained with different optimization algorithms and clipping techniques are presented. Figures 14a, 14b, and 14c display the loss landscapes of the models at epoch 10, batch 6, for 3 distinct experiments. Each figure plots the loss against the step size, showcasing the optimization trajectories of various algorithms, including stochastic gradient descent, SGD, Adam, Lion, sine SGD, and normalized SGD, with and without gradient clipping and update clipping. The experiments demonstrate that Adam and Lion converge to similar loss values, while SGD and its variants exhibit higher losses. The addition of gradient clipping and update clipping techniques improves the convergence of these algorithms. Lion outperforms Adam in terms of convergence in experiment 2, and the application of update clipping further enhances the performance of Lion. Sine SGD and normalized SGD exhibit inferior convergence compared to other algorithms. The results also provide insight into the optimization process of the Adam algorithm, illustrating the complex nature of the loss landscape. Overall, these experiments provide a comprehensive analysis of the loss landscapes of machine translation models, shedding light on the effectiveness of different optimization algorithms and clipping techniques in improving model convergence. The comparison of optimization algorithms for machine translation tasks involves stochastic gradient descent, SGD, Adam, Adafactor, Lion, sine SGD, and normalized SGD. Experiments are conducted with different clipping strategies for gradients and updates to assess their impact on model convergence and stability. Clipping gradients at 0.1 improves the stability of SGD in Adam, while Lion and its variants exhibit more robustness against gradient explosions. Update clipping at 0.5 further enhances the stability of Adam and Lion. The optimization landscapes of machine translation models using Adam are visualized, showcasing the convergence behavior and the role of clipping strategies in navigating complex loss landscapes. This analysis provides a detailed understanding of optimization algorithms and clipping strategies in deep learning, highlighting their strengths and limitations in different scenarios. In machine translation, the choice of optimization algorithm and clipping strategy significantly impacts directional sharpness, a critical metric for model performance. To investigate this, an experiment was conducted comparing the directional sharpness of 6 optimization algorithms: stochastic gradient descent, SGD, Adam, Adafactor, Lion, sine SGD, and normalized SGD. Each algorithm was evaluated with and without gradient clipping and update clipping across 3 experiments. The results, presented in the table, show the ratio of directional sharpness for each algorithm relative to SGD, calculated for epoch sizes ranging from 2 to 20. In general, Adam and Adafactor exhibit higher directional sharpness ratios compared to SGD, particularly when used with gradient clipping. In contrast, Lion and sine SGD demonstrate lower directional sharpness ratios, while normalized SGD shows intermediate values. The epoch size has a significant impact on the directional sharpness ratio, with smaller epoch sizes leading to higher ratios. The use of gradient clipping and update clipping can also significantly affect the directional sharpness ratio, depending on the optimization algorithm used. These findings provide valuable insights into the relative directional sharpness of different optimization algorithms and clipping strategies, informing the design of machine translation models and their optimization strategies. The optimization techniques employed in various deep learning algorithms are crucial for efficient training. The page focuses on the step size and loss values across different epochs and batches, comparing the performance of SGD, Adam, Adafactor, and Lion optimizers. It highlights the impact of gradient clipping on loss values, emphasizing the significance of choosing the right optimizer and its parameters. The comparison in Table 7 highlights the directional sharpness ratios of various optimization algorithms relative to stochastic gradient descent, SGD, on the autoregressive task in the atom trajectory. The directional sharpness ratio measures the alignment between the update direction and the gradient direction. ADA factor and its variant with gradient clipping exhibit higher ratios than atom and its variant, especially at fewer epochs. Lion demonstrates lower ratios across all epochs. Notably, ADA factor with gradient clipping achieves a ratio of 4.66 times 10^7 at 2 epochs, indicating superior alignment. The inclusion of gradient clipping significantly impacts the directional sharpness ratio, particularly for atom and ADA factor, leading to improved alignment. These findings suggest that the choice of optimization algorithm and its hyperparameters substantially influences the directional sharpness of updates, affecting convergence and performance. The discussion section reveals the coherence of observations across various tasks, model architectures, iterations, and local geometry. Directional sharpness exhibits relative stability for the same task across iterations, and coordinate-wise clipping consistently improves sharpness and finds a better direction to optimize. The trade-off between directional sharpness and gradient correlation is explored, highlighting that minimizing directional sharpness is crucial for decreasing loss, but having the lowest sharpness does not guarantee fast loss decrement. ADA factor, for instance, consistently exhibits the lowest directional sharpness but often fails to find a good direction to optimize, resulting in poor performance. This underscores the insufficiency of merely minimizing directional sharpness for an optimization algorithm to work well. Gradient correlation is also essential for the convergence of optimization algorithms. The effect of trajectory on the performance of different optimization algorithms is another key point. Different algorithms can follow distinct trajectories and converge to different minima in deep learning. The local geometry of adaptive algorithms can implicitly select the trajectory with good smoothness. Landscape visualizations demonstrate that ADA factor performs well in the SGD trajectory but not in the atom trajectory on the machine translation task, indicating that different optimization algorithms have local geometry with distinct properties. However, atom's good performance and significant outperformance of SGD in almost all cases suggest that trajectory may not be the primary explanation for atom's excellent performance in practice. The experiment on the smoothness of Hessian, conducted using a standard BERT model for binary text classification tasks, employs the Gauss-Newton matrix to approximate the Hessian of the neural network. This approximation is essential in understanding the curvature of the loss function. The Gauss-Newton Hessian approximation is computed using the Jacobian of the logits and the second-order derivative of the cross-entropy loss function, resulting in a positive semi-definite matrix. Its square root is derived, and in the case of a two-dimensional output space, the exact formula for the second-order derivative of the cross-entropy loss function is calculated. The Hessian matrix is then approximated as the outer product between the gradient of the neural network with respect to its parameters and the gradient itself, resulting in a rank 1 matrix. For any batch S, the Hessian is computed as the average of the outer products of the gradients, and its spectral norm is determined by the spectral norm of a Px, S, matrix. The experiment setup includes using the PyTorch framework, the Hugging Face implementation of BERT, and a pre-trained BERT for sequential classification model. The learning rate is set to 10 to the power of 4, and the batch size is 25. This setup allows for a larger batch size due to the low dimensionality of the output space in binary classification tasks. The experimental results for the smoothness experiment are presented in Table 8. To remove noisy coordinates, the authors eliminate all coordinates with row norms at least 4 times the mean of the row norms, resulting in the removal of 1% to 2.5% of the coordinates. This process significantly improves the smoothness of the function, with a 2 to 3 times improvement in smoothness compared to the full function, consistently across all batches and epochs. This validates the definition of robust smoothness and demonstrates that optimizing most coordinates under the robust smoothness setting is feasible. The table displays the results for various epochs, including the spectral norm of the full Hessian, L, the fraction of removed coordinates, epsilon, and the spectral norm of the remaining Hessian, L. Specifically, at epoch 0, the spectral norm of the full Hessian is 3582.06, with a fraction of removed coordinates epsilon equal to 0.0159, resulting in a spectral norm of the remaining Hessian L of 2.91. Similarly, at epoch 1, the spectral norm of the full Hessian is 2892.63, with epsilon equal to 0.0114, resulting in L of 3.21. The results for epochs 2, 7, 8, and 9 are also presented, showcasing the consistent improvement in smoothness across different epochs. In this supplementary experiment, we delve into the directional sharpness of ResNet 152 on the CIFAR10 dataset. The findings, as presented in Table 9, reveal that adaptive algorithms can exhibit significantly higher directional sharpness than stochastic gradient descent, SGD. This contradicts the observations made in the transformer architecture, suggesting that the property discovered is not universal but rather specific to certain architectures. This study employs a batch size of 1000 and computes the directional sharpness under the same settings as described in Appendix B. The table showcases various optimization algorithms, including SGD, ATOM, ADAFactor, Lion, Sine SGD, and normalized SGD, with and without gradient clipping at a threshold of 0.1. For each algorithm, the ratio of directional sharpness is calculated, with a ratio of 1.0 representing the directional sharpness of SGD. As evident from the table, adaptive algorithms such as ATOM and ADAFactor exhibit higher directional sharpness than SGD across different epochs. Interestingly, the addition of gradient clipping reduces the directional sharpness for most adaptive algorithms, although it does not completely eliminate the difference. This study highlights the importance of considering the interplay between the model architecture and the optimization algorithm when analyzing the directional sharpness. It also underscores the need for further research to understand how different architectures influence the optimization process and the implications for model performance.